Hello everyone and welcome back to this video on the TheCodeBakery. So in this video I'm going to be going over Codeforces Round 660, Division 2, Problem D, which is called Captain Flint and Treasure. So I'll provide the link to the problem statement below so you guys can try this problem for yourself. And I'd highly recommend all of you guys read this problem first and at least give it some thought and maybe try to create a code to help to solve this problem. But for this video, I'm just going to go over the solution, so if you guys haven't done that, I'd recommend you guys do it right now, but let's just get into the solution. So in this problem, we can essentially transform these two arrays into a directed graph. And they also say that they won't have any cycles, so this is essentially going to be a directed acyclic graph, such that we try to remove all of the nodes and get the largest possible sum. So okay, how are we going to do this? So one thing that's important to know is this term called topological sort. So let's see, my handwriting is pretty bad. I'll just provide a link to like probably like a Geeks for Geeks article about topological sorting, but I will essentially explain it very briefly. So topological sorting can only be used in a directed acyclic graph, and it's where we order the nodes such that we are never going to go from a higher node to a lower node, or a lower node to a higher node. So for example, a topological sorting in this graph would be 1, 2, 3, 4, 5, 6. So as you can see in this graph, we are never going to go from a lower position, or we're never going to go from a higher position to a lower position. So topological sorting, like I said before, can only be used on graphs that are directed and acyclic. So if you see that your problem probably has a directed acyclic graph, you're probably going to start thinking about topological sorting. So alright, how are we going to do how do we implement topological sort? So I'm just going to go over this also pretty briefly, but essentially what we have is you essentially are going to implement a queue that contains like all the nodes that have no what's it called? No edges going to it. So in this case, we only have in the beginning node 1 in our queue. So then we assign this to the current number, so this would be 1, and we remove all of the edges that are going from one to another node. So we're essentially going to be removing this node. Now we remove it from the queue, and then we put in the nodes that currently have no edges going towards it. So in this case it would be 2 and 3. So we then number 2. So I'm actually going to keep this, but I'm going to put it in green. So we put number 2 as the second node, and we erase the edges going from 2. So again, these are represented as green, so like we removed it. And we put in the nodes that currently have no edges going towards it, which in this case is only 5. And we remove 2 from the queue. And yeah, this would essentially keep on going. So then we would have, this one would be 3, this one would be 4. We would remove both of these edges, so this one and this one. And then now currently node number 4 has no edges going towards it. So this one would be number 4, or this one would be number 5 because we already have a something as number 4, and then remove this edge and number it with number 6. So that is how we get a topological sorting. And one thing to know is that topological sortings kind of can change, such that this one could be 2 and this one could be 3, but the main idea still sticks, is that we're never going to go from a higher ordered node to a lower ordered node. Alright, so now that we know what topological sorting is, how can we solve this problem? So essentially, what we can do for this problem is we can go through the topological ordering. So like each each node is like given a value, and it's also kind of like given, yeah, it's each node is given a value. So let's just like order these let's give a number to each of these nodes. So this could be 3, this could be like -2, this could be like 1 over here, this could be -4, 7, and 2. Alright, so now we're going to go through the topological ordering, which is represented by the blue numbers. So I first go to 1 and I say, alright, is this, and we're essentially going to give it like a new topological ordering, because the problem is that we don't want a negative number to be added to something that has like, we don't want a negative number to be added to anything, because that's going to decrease our sum, and we want to maximize the possible sum we have. So we have to deal with these ones that have negative numbers differently. So I'm just going to give the new topological ordering kind of as like the green numbers. So I first go to the first number in the topological ordering and I say, alright, this is a positive 1. So this is one is fine right here. So this is now 1, and then just like before, I'm essentially going to go to these ones, or actually, in our problem, we're actually not going to have like we're not going to have it so that there can be more than one edge going from a node. So I'm probably going to have to create a completely new graph. So let's just go like over here. So I'm just going to make this a pretty standard one. So like it would be like 1, 2, and then we can put this as like 3 over here. Or actually this could be, the topological ordering could be 4. So again, this is just the topological ordering, assuming that we already got it. And then this is to a 3 right here. So I'm just going to number these. So this one could be 2, 3, -5, and 2. So these are the values associated with it. So I'm going to go through each of the topological ordering, and I'm going to say, alright, is the current one positive or negative? If it's positive, then I'll just give it the current lowest number that you can give it. So in this case, it would be 1, and I'm going to see if it does have an edge going to another one, and if it does, I'm going to add it to that node's number. So in this case, it would be, actually it would be 5, because I think I put a 3 before. So now this would be a 5, and essentially this node has disappeared, and I'm going to go to the second one now. So the second one also has a value of above 0. So I'm going to order it with the number 2, and I'm going to add it to the one that it connects to. So in this case, 5 plus 2 is 7, so I have a 7 right here. Now I'm going to go to the next one in the topological ordering. So the next one is number 3, but this one is a -5. I do not want to add this to the one that it's going to connect to, because that's going to just lower our sum. And by the way, I should also probably have a sum variable over here. So sum is currently 2 plus 5, so 7. But yeah, I don't want to add this -5 to this node right here, because that's going to lower our sum. So instead, I'm going to give this the highest possible topological ordering. So in this case, that would be 4. And I mean, like, it doesn't matter when like I add it, but like I can just add it right now. So now our sum would be 2. And then I would go to the next one in the topological ordering. So this one is a positive number, so it's 7. So I'd add that to our current sum, and our sum is now 9. And this one would have the order number of 3. So yeah, you could either first find the new topological ordering and then just like simulate it, like repeat it again, but like you can just add the number once you see it. But like in this case, as you saw, if it's like -5, then obviously I'm not going to add it over here. I'm just going to give it the highest possible ordering, add it to our sum, but do not add it to this node right here. So then in the end, we have this new topological ordering. So we would go 1, 2, 4, 3. So that would be the order that we add the nodes in, and then we have our sum. So this is the entire solution. I'll provide my code solution in the description below if you guys want to check that out. And hopefully you guys can also watch other videos on the Code Bakery. And thank you, goodbye.